As we know, the optical waveguides can guide the wave by the total internal reflection. And consider a waveguide here. We have the Coe index N1 and the cladding index N0. Of course, N1 is larger than N0, and here is the index curve for the optical waveguide. The Coe size is 2a, and we have the corresponding reflective index curve like this. And we want to transmit signal from the air to the waveguide. Consider a signal with the angle theta to the waveguide axis, which is z, and we want to launch this signal into this waveguide. As the signal goes into the waveguide, the corresponding reflection angle is phi. And as the signal goes to the interface between the Coe and the cladding, due to the total internal reflection, it will reflected, and to another interface, it will be reflected again, and by the total internal reflection, the signal can be transmitted from the input to the output to perform the transmission of the information. Okay, so at this interface, we shall have TIR happen, and if this angle is phi, we can know that this angle will be half pi minus phi. Okay, and of course, to make this happen, we must satisfy the total internal reflection at the Coe cladding interface. To satisfy the TIR at this interface, we must have light N1 times psi half pi minus phi should be larger than N0 times 1. Okay, so at this interface, we must make this condition satisfied, then we can have the total internal reflection. And from this condition, we can say that the sign here can be expressed as cosine phi. So we say cosine phi must be larger than N0 divided by N1. Since cosine phi must satisfy this condition, we can say that sine phi should be smaller than square root of N1 square minus N0 square divided by N1. So from the total internal reflection condition, we can have that sine phi should satisfy this condition. Okay, then we go to the input port here. At the input port, the signal with theta to the waveguide axis is launched into the waveguide. So at this interface, it must satisfy the Snell's law. We can have light 1 times sine theta should be equal to N1 times sine phi. Okay, this equation comes from the Snell's law. And we have no light. To have TIR happen, the sine phi should be smaller than this value. So take this condition into here. You will have light sine theta should be smaller than square root of N1 square minus N0 square. So this condition tells us that if you want to transmit signal from the air to the waveguide, and successfully induce the TIR at the co-cladding interface, the input angle theta should be satisfied that sine theta is smaller than this value. And this means that the input theta should be smaller than arcsine square root of n1 square minus n0 square. Okay, so to efficiently induce the TIR here, the theta have the maximum value. So theta maxima will be arcsine square root of n1 square minus n0 square. Okay, this means that the theta here, the input angle theta here, should be smaller than the theta max. If the theta is smaller than theta max, then as it into the waveguide, it can induce the TIR. But if theta is larger than theta max, as the signal input into the waveguide, it cannot induce TIR here. So part of the power will be transmitted to the cladding, and it will have high losses. Okay, so theta max here is defined as the maximum light acceptance angle for the waveguide. For incident angle smaller than theta max, it can input into the waveguide to induce TIR. For incident angle larger than theta max, it cannot induce TIR, so it cannot be transmitted by the waveguide. So theta max is defined as the maximum acceptance angle for the light wave for the waveguide. Okay, and such kind of the theta max, we call it a very important physical parameter. We call it numerical aperture. Which is also called NA. So if you read some papers and you see the word numerical aperture or NA, this means that the maximum acceptance angle for this waveguide. We then define a very important parameters. Here, we define the refractive index difference between N1 and N0, which is delta is N1 square minus N0 square divided by 2N1 square. This is a very important parameter for optical waveguide. And according to the expression, the term here, it can be written as N1 plus N0 times N1 minus N0 divided by 2N1 square. And usually for optical waveguides, we will have N1 is almost the same as N0. For if we have this condition, then this term can be written as 2N1, right? So divided by with this one, we will have the delta will almost to be N1 minus N0 divided by N1. So if N1 is almost the same with N0, you can find out the refractive index difference by this equation. Okay? Then according to the definition here, the numerical aperture NA, which we have said it is theta maxima, is defined as outside square root of N1 square minus N0 square. And as N1 is almost the same as N0, we can rewrite NA. NA is approximately to be square root of N1 square minus N0 square, and it can be expressed as N1 times square root of 2 delta. Here I will show you two examples. Consider a multi-mole fiber. We have the co-index N1 to be 1.467 and the cladding index is 1.4525. For such kind of multi-mole fiber, you will have the refractive index difference is 1.4%, and we will obtain the numerical aperture to be 11.8 degree. But for single mode fiber, we have the co-index is 1.46 and the cladding index N0 is 1.4525. For such kind of device, we have the refractive index difference is 0.2%. As a result, we have a smaller numerical aperture to be 0.092 degree. And from these two results, you can see that if you want to transmit signal into the single mode fiber, the acceptance angle is very small, so you have to align the line with the fiber very precisely. But however, for multi-mode fiber, the acceptance angle is relatively large. So if you want to receive signals by the fiber, the better way is to choose multi-mode fiber.